Hello everyone, welcome back to another Organic Chemistry 1 learning task video. So for this learning task, we are going to deal with radical reactions, aromatic compounds, and aromatic compound reactions. So for this problem 11.49, consider the following radical process called a thiolene coupling reaction in which an alkene is treated with a thiol RSH in the presence of the radical initiator. So this is the reaction or the net reaction, and in this reaction, two groups Rs and H are being added across the pi bond in an anti-Marconical fashion. This reaction resembles the anti-Marconical addition of HBr across a pi bond. Using this reaction as a guide, we can draw the following initiation and propagation steps. We know that a thiolene coupling reaction occurs in three steps. So first is the initiation steps. For the initiation steps, the initiator could be a hydrogen or peroxide that will form a free radicals. So for this step, there's a formation uh, of the free radicals. So for the second step, the reactive end of chain adds to the alkene or to a pi bond forming larger free radical calling as the chain propagation. So for this step, the the S the SR bond or the SR is being added to the alkene or to the pi bond. For the third step of the reaction or for the radical reaction, this step is the propagation step 2. For this propagation step 2, there will be a hydrogen abstraction to regenerate the Rs radical. So from the earlier product from the propagation step number 1, SHR or RSH will be added, or the thiol will be added to the product earlier. This process will call the hydrogen abstraction since the hydrogen was being added to the product earlier to form or to regenerate the Rs radical. So as you can see, this step will lead us or will yield us to our desired product plus the regenerated Rs radicals. So note that in radical reaction, we are using a single hook arrow or the fish hook arrow to show the formation of the radicals. So problem 18.54, azulene exhibits an appreciable dipole moment and an electrostatic potential map. Indicates that the 5-membered ring is electron-rich at the expense of the 7-membered ring. So as you can see from this picture, azulene exhibits an appreciable dipole moment. In chapter 2, we saw that a resonance structure will be insignificant if it has carbon atoms with opposite charges. Azulene represents an exception to this rule because some resonance structures with C resonance structures exhibit aromatic stabilization. With this in mind, draw resonance structures of azulene and use them to explain the observed dipole moment. So what are we going to do on this problem is to draw a resonance structure of azulene and then explain it or use that resonance structure to explain the dipole moment. This is not a reaction of problem, but we will going to show the mechanism of forming the resonance of the azulene. So, each of the rings in the following resonance structure is aromatic. Therefore, it contributes significant character to the overall resonance hybrid, giving the azulene a considerable dipole moment. So as you can see on this structure or this compound, the resonance structure is aromatic since we know that the aromatic compound has an odd number of pi bonds or an odd number of the double bonds. So therefore, it contributes significant character to the overall resonance hybrid. So for the mechanism, the pi bond from so for the mechanism of the formation of the resonance structure of the azulene, this bond will break, then forming a double bond on this bond. Then this bond will break also, forming another double bond. Then this bond will break and forming another bond, and this bond again will break, forming another bond. This carbon will form a carbon and ion, and this carbon will form a carbon cation. So from the mechanism, or from the mechanism of the formation of the bonds, the resonance structure of the azolene is like this. There is a carbon ion and the carbocation. Therefore, this compound will have a significant dipole moment in contrast. In contrast, the other compound does not have a resonance structure in which both rings are aromatic. So to answer the question, this compound will have a significant dipole moment. So moving on from our third problem. So for the last problem, or for the problem 19.40, draw the most likely mechanism for each of the following transformation. So the reaction is the product is 1 amino 4 nitrobenzene from the 1 iodo 4 nitrobenzene using a sodium amide and water. So note that the reagent sodium amide is a powerful nucleophile, and the three criteria for SNA or for SNAR or for the aromatic nucleophilic substitution or nucleophilic aromatic substitution are met, which are one, a nitro group, and two, a living group that are both para to each other. So as you can see, the 1 iodo for nitrobenzene has a nitro group and a living group that are para to each other. So note that our sodium amide is a powerful nucleophile, therefore it will attack the the aromatic ring, generating a resonance stabilized structure, so that the sodium amide will attack the aromatic ring, then forming a carbon ion, leading to the resonance stabilized intermediates. So this is the intermediates. As you can see from the last, or for the fourth intermediate, there is a loss of a living group. That is the second or the last step for this reaction that will give us the product. So as you can see, the product is the product now has no living group, forming a amino and the nitrobenzene. So thus, in order to so for the summarization, in order to form a 1 amino for nitrobenzene, we will use the sodium amide and water to react with the 1 iodo or for nitrobenzene. So that's it for our learning task today. I hope you learned something, and if you have questions or clarifications, just comment it down below on a comment box. Thank you and good day.